Tonight, we're going to travel to every planet in our solar system. We're going to look at what it actually takes, the real physics, the real missions, the real numbers to cross the space between Earth and each world in our cosmic neighborhood. And here's what most people don't realize. The answer is never a single simple number. It changes depending on where you're going, how fast you're traveling, what the planets are doing at the moment you launch, and what you're trying to accomplish when you arrive. And the distances are so large that even our fastest spacecraft take years to cross them. Imagine what that means for a person inside one. By the end of tonight, you're going to understand the real transit time to every planet in this solar system and what it actually takes to survive the journey. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a diagram you've almost certainly seen at some point in your life. The solar system, laid out flat on a page or a screen. The Sun on the left, Mercury closest in, then Venus, then Earth, then Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, all arranged in a neat, orderly row that fits comfortably in front of you. That diagram is useful. It gets the order right. It shows you which planets are closer to the Sun and which are farther. But it has done something to your intuition that needs to be corrected before any of the travel times we're going to discuss will make sense. Every single solar system diagram you have ever seen is not drawn to scale, not even close. The planets would be invisible if the diagram were accurate. If you tried to draw the solar system to true scale, with the Sun the size of a basketball, Earth would be a grain of sand less than 3 feet away. Jupiter would be a marble about 15 feet from the Sun. Neptune would be another marble, about 450 feet away. And those are just the planets. The Oort cloud, the outermost boundary of the Sun's gravitational influence, would extend to about 30 miles away from that basketball. 30 miles. And the nearest star, Proxima Centauri, would be on the other side of the planet. This is the solar system at true scale. And in that context, the travel times we're about to discuss stop being abstract numbers. They start feeling like what they actually are: real distances, real emptiness, real time. Before we start moving through the solar system, there's a second thing to understand. Spacecraft don't travel in straight lines. They can't, because there are no roads in space, and because the physics of orbital mechanics don't work that way. To get from Earth to another planet, a spacecraft follows a curved arc through space, a path determined by the gravitational pull of the Sun, the initial velocity provided by the launch rocket, and the relative positions of the two planets at the time of launch. The most common type of path used in planetary missions is called a Hohmann transfer orbit. Named after the German engineer Walter Hohmann, who described the concept in 1925, a Hohmann transfer is an elliptical arc that begins at one orbit and ends at another, using the Sun's gravity to curve the spacecraft along the path. These transfers are fuel efficient. They minimize the amount of propellant needed to travel between two orbits. But efficiency has a cost. Hohmann transfers are slow, and they only work cleanly when the two planets are aligned in very specific positions relative to each other at the moment of launch. The window of opportunity for a Hohmann transfer to Mars, for example, opens only once, approximately every 26 months. The planets align, the window opens for a few weeks, and then it closes. Miss the window, and you wait more than 2 years for the next one. The planets don't reorganize their orbits to accommodate a delayed launch. There's also the complication that every planet is moving. Earth is orbiting the Sun at about 67,000 miles per hour. Mars orbits more slowly, at about 53,000 miles per hour. A spacecraft launched from Earth doesn't aim at Mars. It aims at where Mars will be when the spacecraft arrives. The trajectory is a calculation of motions across months or years, refined with precision that would have seemed like pure mathematics to anyone before the space age, but which is now standard mission planning. This is why reaching any given planet requires both timing and geometry, and why the travel time to the same planet can vary significantly from mission to mission depending on when the launch occurs. So let's go. Starting with the planet that geography says should be easiest. Mercury is the smallest planet in the solar system and the closest to the Sun. It orbits at an average distance of about 35.9 million miles from the Sun. Earth orbits at about 92.9 million miles. So Mercury is inside our orbit, not outside it. That changes everything about how you get there. You might assume that because Mercury is closer to the Sun, it's easier to reach. It's not. Mercury is one of the most challenging destinations in the inner solar system, and for a reason that feels deeply counterintuitive. To reach Mercury from Earth, you don't need to speed up. You need to slow down. Here's why. Earth orbits the Sun at about 18.5 miles per second. Mercury orbits the Sun much faster, at about 29.4 miles per second. When you launch a spacecraft from Earth, it starts out traveling with Earth at roughly Earth's orbital speed. To fall inward toward Mercury's orbit, the spacecraft needs to lose speed relative to the Sun. Gravity will do some of the work, but not enough. You have to burn fuel to shed velocity. And then, when you arrive at Mercury's orbit, you're moving far too fast to enter orbit around this small, low-gravity world without burning even more fuel. Mercury's low gravity means its sphere of gravitational influence is small. Slowing down into orbit requires a massive fuel expenditure. This is why missions to Mercury are rare, and why the ones that do go are engineering achievements that don't get nearly enough recognition. NASA's Messenger spacecraft launched in August of 2004 and arrived at Mercury in March of 2011, that is 6.5 years, to reach the closest planet to Earth. Messenger didn't fly in a straight line. It needed multiple gravitational assist maneuvers, swinging past Earth once, Venus twice, and Mercury itself 3 times before finally slowing down enough to enter orbit. Each flyby used the planet's gravity as a free brake, bleeding off speed without burning extra fuel. Without those assists, the fuel requirements would have made the mission impossible. The European Space Agency's Bepi-Colombo mission, launched in October of 2018, is on an even more complex trajectory. It uses Earth once, Venus twice, and Mercury 6 times for gravity assists before entering orbit around Mercury in late 2026. 8 years for a destination that is, at its closest approach to Earth, about 48 million miles away. Bepi-Colombo is actually 2 spacecraft traveling together, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, that will separate when they arrive and orbit the planet at different altitudes, studying different aspects of Mercury's environment. A crewed mission could theoretically go faster by carrying more fuel and burning it more aggressively. The fastest theoretical transfer to Mercury, using a relatively direct-powered trajectory, could get a spacecraft there in around 3 to 4 months. But that approach requires far more fuel than current technology can deliver efficiently. And the thermal environment near Mercury presents challenges unlike anything encountered elsewhere in the inner solar system. Sunlight at Mercury is about 5 to 11 times more intense than at Earth. The Sun, seen from Mercury's surface, appears about 2.5 times larger in diameter than it does from Earth. The surface temperature on the Sun-facing side reaches around 800 degrees Fahrenheit, which is about 427 degrees Celsius. The dark side drops to about negative 290 degrees Fahrenheit, which is about negative 179 degrees Celsius. There is no atmosphere to moderate between those extremes. The temperature differential between the daylit and dark hemispheres is one of the largest in the solar system. Mercury also has an extremely slow rotation. It rotates once every 59 Earth days, completing 3 rotations for every 2 orbits around the Sun. A solar day on Mercury's sunrise to sunrise lasts about 176 Earth days. The planet is tidally locked in a 3-to-2 resonance with its orbit, a gravitational relationship with the Sun that has persisted for billions of years. For a crewed mission to Mercury's surface, the thermal management challenges are severe enough that no current spacesuit or surface habitat design is rated for them. You would need to operate during the brief transition zones, the terminators, where day meets night, or deep in permanently shadowed polar craters, where water ice sits frozen in regions of eternal darkness. Mercury has polar ice deposits in permanently shadowed craters at both poles. Water ice on the planet closest to the Sun. The ice survives because the craters are deep enough that sunlight never reaches the bottom. It is a strange and specific kind of hospitable places where humans could theoretically stand without being roasted. But they are small and cold, and the rest of the planet wants to bake everything. Any crewed mission to Mercury's surface would have to deal with thermal extremes that exceed anything humans face anywhere else in the inner solar system, combined with a radiation environment that lacks even Mars's thin atmospheric protection. The practical reality for a human mission to Mercury, if one were ever attempted with near-future technology, is somewhere between 4 months and 1 year, depending on trajectory and energy budget. The European Bepi-Colombo orbiter will study Mercury's surface, interior, and exosphere in detail, and return data that will shape what any future mission would investigate. The science will be there. The motivation to go will be there. The technology, if it develops as propulsion engineers hope, may eventually make it practical. There are currently no plans for a crewed Mercury mission. There are not even detailed architectural studies. The planet that is closest to Earth turns out to be one of the least hospitable to visit and one of the most fuel expensive to reach. It is both nearest and farthest in its own perverse way. Venus is different. Venus orbits the Sun at about 67.2 million miles. It is the planet that comes closest to Earth of any body in the solar system at certain points in their respective orbits, approaching within about 24 million miles. Unlike Mercury, Venus is a large world with strong gravity, which actually helps a spacecraft break into orbit. The Hohmann transfer to Venus takes about 3.5 to 4 months. Real missions have confirmed this. Mariner 2, launched in August of 1962, arrived at Venus in December of 1962. 109 days. About 3.5 months. That is the benchmark. More recent missions followed similar profiles. Venus Express launched in November of 2005 and arrived in April of 2006, about 5 months. The JAXA mission Akatsuki, launched in May of 2010, missed its orbital insertion burn and spent 5 years wandering in a solar orbit, before successfully entering Venus orbit in December of 2015. That's a longer story, involving a hardware failure and the creative use of small thrusters to try again years later. But the fundamental transit time is the same, a few months. A crewed mission to Venus would take roughly the same amount of time for the outbound leg, 3 to 5 months. So in terms of transit time, Venus is genuinely the most accessible planet. The problem is not getting there. The problem is everything else. The moment you look past the transit time and start asking what you'd actually do when you arrived, Venus becomes something close to a nightmare. The surface of Venus sits under 93 times the atmospheric pressure of Earth. That is the equivalent of being about 900 meters beneath the ocean surface. Every Soviet lander that touched the surface of Venus survived for between 23 minutes and 2 hours before being destroyed by the combination of pressure, heat, and corrosive chemistry. The surface temperature averages about 867 degrees Fahrenheit, which is about 464 degrees Celsius. Hotter than Mercury, at its hottest, despite Venus being farther from the Sun. The reason is the planet's thick carbon dioxide atmosphere, which traps heat through an extreme greenhouse effect that has been running for billions of years. The atmospheric chemistry includes clouds of sulfuric acid droplets at concentrations up to 80% sulfuric acid by mass. Not traces, not hints. Dense clouds of concentrated sulfuric acid, sitting at altitudes between about 30 and 40 miles above the surface, completely obscuring the ground. Below the cloud deck, the atmosphere is hot and dense and chemically hostile to anything we can currently build for long durations. The wind at the surface is relatively slow, only a few miles per hour, but at 93 times Earth's atmospheric pressure, even a gentle breeze carries the force of a fast-moving river current against any structure in its path. No material we currently have can survive on Venus's surface for more than a few hours. We have no spacesuit capable of protecting a human in that environment. We have no technology that would allow a human to step out of a lander and return in any meaningful sense. A crewed mission to Venus means orbiting it, or floating in its upper atmosphere. The upper atmosphere, at around 31 to 37 miles above the surface, is one of the strangest and most counterintuitive places in the solar system. It is the most Earth-like environment anywhere outside Earth itself. Temperatures there range from about 32 to 167 degrees Fahrenheit, depending on altitude, which is about 0 to 75 degrees Celsius. Pressure is close to sea level on Earth. Humans could theoretically float at that altitude in a habitat without needing a pressure suit. What they would need is a breathing supply, because the atmosphere is carbon dioxide and nitrogen, not oxygen. And they would need protection from the sulfuric acid cloud particles that exist at precisely those altitudes. Materials capable of surviving prolonged exposure to concentrated sulfuric acid under those temperature and pressure conditions are a genuine engineering challenge. Acid-resistant polymers, certain fluoropolymers, and ceramics have been studied for Venus atmospheric missions. The concept of a crewed Venus cloud habitat, an airship floating at altitude, conducting science, potentially even serving as an operations base for surface robotic missions, has been studied seriously. NASA's high-altitude Venus operational concept, known as HAVOC, looked at exactly this architecture. Crewed airships in the cloud layers. Robotic landers controlled from above, reaching the surface briefly and returning data before the environment destroys them. It is a mission concept that fits the unique combination of accessibility and hostility that Venus presents. Close enough to reach in a few months. Fascinating enough scientifically to be worth going. Impossible to touch at the surface with current technology. Venus also holds a planetary science mystery that makes it scientifically compelling beyond the general interest of visiting another planet. Venus and Earth are nearly the same size. Nearly the same mass. They formed in similar regions of the solar system from similar material. They are, in many respects, twins. And yet one is a living, water-covered, life-bearing world, and the other is a scorched, pressurized, acidic furnace. Understanding what went differently on Venus, what chain of events or conditions turned an Earth-like beginning into a Venusian outcome, is directly relevant to understanding the habitability of planets around other stars. The atmospheric loss processes on Venus, the feedback mechanisms that drove its runaway greenhouse effect, the timing and causes of whatever fate befell any ancient water it might have had. These questions have implications far beyond Venus itself. Venus is, in a real sense, a warning sign that happens to orbit our own star. The transit time to Venus is 3 to 5 months. Easy. It is the destination that resists. Now we come to Mars. Mars orbits the Sun at an average distance of about 141.6 million miles. If there is one destination in the solar system that has captured the imagination of serious mission planners, engineers, space agencies, and private companies more than any other, it is Mars. Mars is the most plausibly reachable world with a solid surface that humans can walk on. It has a thin atmosphere, about 1% the density of Earth's, mostly carbon dioxide, thin enough that you cannot breathe it, but substantial enough to create weather, dust storms, frost cycles, pressure variations across its surface. It has seasons, because its axial tilt of about 25 degrees is close to Earth's 23.4 degrees. A Martian day called a sol is 24 hours and 37 minutes. Almost exactly an Earth day. This is one of those facts that feels too convenient to be real, but it is real. A human on Mars would experience days and nights nearly identical in length to what they experience on Earth. There is no jet lag of the circadian kind. Mars has polar ice caps at both poles. The North Polar Cap is mostly water ice beneath a seasonal layer of carbon dioxide frost that accumulates in winter and sublimates in spring. The South Polar Cap has a permanent water ice core as well, covered year-round by a thicker carbon dioxide ice deposit. Ground ice water, frozen in the soil, has been confirmed to exist at mid-latitudes, detected by instruments aboard orbiters and confirmed by landers. NASA's Phoenix lander, which touched down near the North Polar region in May of 2008, directly scraped up and observed water ice a few centimeters below the surface. The Mars Reconnaissance Orbiter has mapped water ice distribution from orbit. There is abundant water on Mars. Not liquid on the surface, the atmospheric pressure is too low and the temperature too cold for liquid water to be stable there. But ice, subsurface brines, and possibly liquid water in deep subsurface environments. There is also evidence in the geology that Mars was once very different. Ancient river channels cut across the surface. Deltas, where rivers once emptied into lakes or seas. Minerals that could only have formed in the presence of liquid water. The Mars that exists today is dry and cold and thin-aired. The Mars that existed 3 to 4 billion years ago may have had a thicker atmosphere, a warmer climate, and liquid water flowing across its surface. Rovers have confirmed these ancient aqueous environments in detailed geological investigations. Curiosity has spent years studying an ancient lake bed at Gale Crater. Perseverance is collecting samples from an ancient river delta at Jezero Crater for eventual return to Earth. What happened to Mars? Something stripped its atmosphere. Without a global magnetic field to deflect the solar wind, Mars lost its atmospheric gases to space over billions of years. The process was slow by human standards, catastrophic by the standards of planetary habitability. In the time frame when life was getting established on Earth, Mars was losing the conditions that might have allowed life to get established there. Whether anything got started before those conditions ended is one of the most important unanswered questions in science. The transit time to Mars in the Hohmann transfer window is about 7 to 9 months, depending on where Earth and Mars are in their respective orbits when the window opens. The two planets align favorably roughly every 26 months. When that window opens, it's typically open for a few weeks to a couple of months. Miss it, and the next opportunity is over 2 years away. Real missions have confirmed the transit range repeatedly. Viking 1 launched in August of 1975 and arrived in June of 1976, about 10 months. Mars Pathfinder launched in December of 1996 and arrived in July of 1997, about 7 months. Curiosity launched in November of 2011 and arrived in August of 2012, 8.5 months. Perseverance launched in July of 2020 and arrived in February of 2021, 6.5 months. The variance reflects both the orbital geometry at launch and the specific trajectory designed for each mission. For a crewed mission, the most thoroughly studied approach is called the conjunction class mission. The crew departs Earth during the opening of a launch window. They spend about 7 to 9 months in transit. They arrive at Mars and conduct surface operations. They must then wait approximately 480 to 550 days, roughly 16 to 18 months, for the orbital geometry to allow a return launch. They then spend another 7 to 9 months returning to Earth. Total mission duration: approximately 2.5 to 3 years from departure to return. That is the number. Not the glamorous one, not the landing. The entire commitment, beginning to end. And within that commitment, the time on Mars is the largest single segment. The waiting for the return window. 500 days roughly. Because the planets will not align for a return launch for that long, and attempting to leave at the wrong time means a trajectory so energetically expensive, it's essentially impossible with any realistic fuel load. The crew cannot leave early. Not if they want to come back. Once you are on Mars, you are on Mars until the solar system says otherwise. This constraint appears in every serious Mars mission design. It is sometimes called the stay time constraint, and it fundamentally shapes what a Mars mission is. It is not an expedition. It is a settlement. Temporary. Planned to be temporary, but in duration more like a posting than a visit. The crew will have to build a life there for those 500 days. They need psychological support structures. They need meaningful work. They need the ability to handle medical situations, equipment failures, and interpersonal conflicts entirely with their own resources. And then they come home, if the mission goes as planned. The transit time itself, 7 to 9 months, presents serious challenges. Before we get into what those challenges are, it's worth being specific about what 7 to 9 months in space actually means physically. The spacecraft itself is the first thing to reckon with. Current habitat designs for deep space proposals range in internal volume, but the realistic pressurized living space for a crew of 4 to 6 on a long-duration mission is roughly comparable to a few modest rooms, perhaps 900 to 1,200 cubic feet of pressurized volume. Sounds manageable until you realize you don't get to go outside. You don't get to see the horizon. You don't get to hear wind or rain or silence that isn't mechanical hum. The International Space Station has about 32,000 cubic feet of pressurized volume for 6 people, and astronauts still describe feeling confined after a 6-month tour. A deep space transit vehicle will be smaller per person, designed for mass efficiency rather than comfort. Same corridors, same surfaces, same smell, same sounds, for months. The days on a long-duration mission have a structure that mission planners design carefully. 8 hours of sleep, with sleeping bags or restraints to keep crew members from drifting. 8 hours of work systems, maintenance, scientific observations, exercise, mission operations. 8 hours of personal time, meals, communication with Earth, recreation. Food on a Mars mission would largely be stored, thermostabilized, freeze-dried, irradiated. Shelf-stable food designed to last years. Palatability is a real concern. Eating the same limited menu of preserved foods for 2.5 years affects morale. Research from Antarctic overwintering studies, submarine deployments, and long-duration spaceflight simulations consistently shows that food quality and variety are among the strongest predictors of crew psychological state during extended isolation. The psychological health of a crew is not a soft concern. It is an operational concern. A crew in poor psychological condition makes worse decisions. A crew with fractured interpersonal relationships can fail to coordinate in emergencies. The food, the schedule, the communication windows with family, the private psychological sessions, these are all mission-critical systems. As important, in their own way, as the propulsion system. Radiation is the primary concern of the transit itself. Beyond Earth's protective magnetic field and the thin Van Allen belts, the crew is exposed to 2 kinds of ionizing radiation. Galactic cosmic rays are high-energy particles that originate from sources outside the solar system. Supernova remnants, active galactic nuclei, other energetic astrophysical events. They stream in from all directions continuously. They cannot be blocked by any practically sized shielding. Their high energy means they penetrate anything we can put on a spacecraft without making the spacecraft impossibly heavy. Solar energetic particles are a different threat. They come from the sun, sudden, intense bursts during solar flares or coronal mass ejections. They are lower in energy than galactic cosmic rays and can be shielded more effectively. But they are unpredictable. A large solar particle event can deliver a dangerous radiation dose in hours. The crew needs a dedicated storm shelter, a small, heavily shielded space within the spacecraft where they go when an event is detected and wait it out. The transit to Mars involves both of these radiation environments continuously for 7 to 9 months. The cumulative dose from galactic cosmic rays alone over a full round trip to Mars is estimated to approach a significant fraction of the career limits currently set for NASA astronauts. This is one reason Mars mission planners have looked at ways to reduce transit time, not just for comfort, but for crew health. Every week, shaved off the transit time is a meaningful reduction in radiation exposure. Bone density loss and muscle atrophy are the second major physiological challenge. In microgravity, bones lose mineral content at roughly 1 to 2% per month in the most affected regions, primarily the hip and lower spine. Muscles that are not loaded lose mass and strength. The cardiovascular system adapts to the reduced demands of a low-gravity environment in ways that temporarily compromise its performance in high-gravity environments. Astronauts, returning from 6 months on the space station, typically cannot walk normally for days to weeks. They need assistance immediately after landing. Their bones take months to return to pre-flight density, assuming they do fully recover. A Mars crew arrives after 7 to 9 months in microgravity and then has to function on a planet. They have to walk, operate equipment, respond to emergencies, all in 37% gravity, which is better than zero gravity for the muscles and cardiovascular system, but the body will have been in zero gravity for the entire transit. The crew needs to be able to function from day one on the surface. Not optimally, but adequately. Mission planners assume a period of adaptation on Mars's surface after arrival. The first days are low activity. Allow the body to adjust. And Mars's lower gravity compared to Earth may actually accelerate adaptation compared to returning to Earth, which is harder on the readapted cardiovascular system. But it remains a significant variable in mission planning. Exercise countermeasures are the primary tool. 2 or more hours per day of structured cardiovascular and resistance exercise throughout the transit, using specialized equipment that works in microgravity. Current space station exercise equipment has been refined over decades. The Advanced Resistive Exercise device uses vacuum cylinders to simulate weight. A treadmill with a harness bungee system keeps the crew member pressed against the running surface. Cycle ergometers provide cardiovascular load. These systems work. They are not perfect, but they meaningfully reduce the rate of deterioration. A crew that exercises rigorously arrives in much better condition than one that doesn't. But they still arrive compromised compared to their baseline. The medical infrastructure on a Mars mission is the third major challenge. The crew carries a physician. They carry medical supplies, diagnostic equipment, surgical capability for basic procedures. What they don't carry is a hospital. An appendicitis on a Mars mission means the crew physician performs the procedure. A bone fracture means crew-managed diagnosis and treatment. A cardiac event means using whatever pharmaceutical and procedural resources the mission carries. Communication with Earth medical teams is possible, but the time delay makes real-time guidance unreliable in any rapidly evolving situation. This is the honest medical reality of a Mars mission. Not catastrophic, necessarily careful pre-mission medical screening, training, and equipment selection address most foreseeable risks. But the margin for error is smaller than any medical situation on Earth. From Mars, the distances multiply. Not gradually, dramatically. The inner solar system, Mercury, Venus, Earth, Mars, occupies a relatively compact region of space. The outer solar system begins at the asteroid belt and extends for billions of miles. And everything out there is cold, dark, far from the sun, and governed by transit times that stop sounding like engineering constraints and start sounding like other categories of commitment entirely. Jupiter is the dividing line. The first giant. Jupiter orbits the Sun at about 483 million miles. The Hohmann transfer from Earth to Jupiter takes about 2 years and 11 months. Nearly 3 years. Real missions have taken various amounts of time depending on trajectory. Pioneer 10, launched in March of 1972, arrived at Jupiter in December of 1973, 21 months, on a fast, direct trajectory. Pioneer 11 made the trip in about 20 months. The Voyager missions, launched in August and September of 1977, arrived at Jupiter in March of 1979 for Voyager 1 and July of 1979 for Voyager 2. About 18 months for Voyager 1 and just under 2 years for Voyager 2, on trajectories calculated to allow continuation to the outer planets. The Galileo spacecraft launched in October of 1989 and arrived in December of 1995, 6 years, using a complex series of gravity assists. New Horizons passed Jupiter in February of 2007, 13 months after its January 2006 launch, but at far too high a speed to enter orbit. It used Jupiter's gravity purely as a slingshot to gain speed for its Pluto mission. For a mission that actually stops at Jupiter, enters orbit, operates in the Jovian system. The transit time ranges from roughly 18 months to 3 years, depending on trajectory and available propulsion. A crewed mission to Jupiter requires solving problems that current technology cannot fully solve. Radiation is the first. Jupiter has the most intense radiation environment of any planet in the solar system. Its magnetic field is about 20,000 times stronger than Earth's. The Jovian magnetosphere is enormous. If it were visible from Earth, it would appear larger than the full moon in the sky, despite being 5 times farther away than the Sun. This magnetic field traps charged particles from the solar wind and from Jupiter's volcanic moon Io, accelerating them to high energies within the radiation belts. The intensity of this radiation varies dramatically with distance from Jupiter. The innermost regions, near Io's orbit, at about 262,000 miles from Jupiter's center, are lethally intense. Electronics designed specifically for Jupiter radiation can still accumulate damaging doses over months. The Galileo spacecraft was radiation hardened, but still suffered significant electronic damage over its mission. Juno, which has been orbiting Jupiter since 2016, follows a highly elliptical orbit that minimizes time spent in the most intense radiation regions. It dips close to Jupiter's cloud tops over the poles, where the radiation environment is somewhat less severe, then spends most of each orbit in the outer reaches of the magnetosphere. Even with this careful orbital design, Juno's electronics are exposed to radiation that rapidly degrades their performance. For a crewed spacecraft, the radiation shielding required to protect human biology in the inner Jovian system would be extraordinary. Current estimates suggest that adequate shielding for the radiation environment near Europa's orbit, about 417,000 miles from Jupiter's center, would require radiation shielding mass that is impractical for any near-future spacecraft. Callisto, the outermost of the four large Galilean moons, at about 1,170,000 miles from Jupiter's center, is situated outside the main radiation belts. The radiation environment there is much more manageable, still elevated compared to interplanetary space, but potentially survivable with conventional spacecraft shielding. A crewed Jupiter mission architecture that has been studied seriously places the crew habitat in orbit around or near Callisto. Robotic missions are then sent closer to Jupiter and to the inner moons. The crew controls these robots. They make decisions. They adapt to findings in real time. But they stay in the relatively safer outer region. Callisto is scientifically interesting in its own right. It may have a subsurface ocean. Its ancient, heavily cratered surface holds a geological record of the outer solar system's early bombardment history. But the scientific prize of the Jovian system is Europa. Europa is about the size of Earth's moon, with a surface of pure water ice. Below that ice shell, estimated to be about 15 to 20 miles thick, is a global liquid water ocean. The ocean is estimated to contain about twice the total volume of all of Earth's oceans combined. It has likely been liquid for billions of years, kept warm by tidal heating from Jupiter's enormous gravitational field. The interactions between the rocky seafloor and the ocean above, particularly at any hydrothermal vents that may exist, could provide chemical energy for life. The arguments for life in Europa's ocean are not wishful thinking. They are based on what we know about life's requirements and how Europa satisfies several of them: liquid water, chemical energy sources, organic molecules, a protected environment stable over geological timescales. The argument against is simply that we don't know. We have never sampled the ocean. We have never gotten a lander to the surface. We have seen the ice shell from orbit and mapped its complex geology, the ridges and bands and chaotic terrain that indicate an active, dynamic environment beneath. NASA's Europa Clipper mission launched in October of 2024 and is traveling toward Jupiter on a trajectory that will bring it to the Jovian system around 2030. Europa Clipper is a robotic mission that will orbit Jupiter, not Europa, making dozens of flybys of Europa at close range to study the moon's surface and ice shell in detail. It is a major step, but it is a flyby mission, not a lander. The questions about Europa's habitability require a surface mission, and a surface mission in the radiation environment of Europa's orbit is one of the most technically demanding missions in planetary science. A crewed mission capable of operating in that environment, either from Callisto with teleoperated surface probes or with direct human presence inside a heavily shielded habitat, is not near-term. But it is the scientific prize of the outer solar system. And getting there, crewed, is nearly 3 years of transit. Saturn orbits the Sun at about 886 million miles. The Hohmann transfer from Earth to Saturn takes about 6 years. Every mission to Saturn has taken at least that long. Pioneer 11, launched in April of 1973 and arrived at Saturn in September of 1979, 6 years and 5 months. Voyager 1 arrived at Saturn in November of 1980, about 3 years and 2 months after its September 1977 launch, using Jupiter for a gravity boost. Voyager 2 arrived in August of 1981, about 4 years after launch, also benefiting from Jupiter. Cassini launched in October of 1997 and arrived in July of 2004, 6 years and 9 months, using gravity assists from Venus twice, Earth once, and Jupiter once. The Cassini mission produced what is arguably the most comprehensive dataset ever returned from any outer planet. 13 years in the Saturn system. Over 600 gigabytes of data. More than 4,000 scientific papers published using its findings. Cassini discovered the plumes of Enceladus. It revealed Titan's complex organic chemistry in unprecedented detail. It characterized the structure of Saturn's rings at a resolution that revealed features smaller than 1 mile across. It discovered new moons. It studied Saturn's magnetic field, its aurora, its complex storm systems. Cassini observed a massive hexagonal storm structure at Saturn's North Pole, a geometric weather system with each side about 8,700 miles long, persistent for decades, the mechanism for which is still not fully understood. Cassini discovered a global ocean beneath Titan's surface, potentially. It watched Enceladus's plumes feed material into Saturn's E-ring. It sampled the composition of those plumes as it flew through them. 13 years. 600 gigabytes. And we are still analyzing what it found. For a crewed mission, 6 years each way means a full round trip spanning at minimum 14 years. A crew member in their late 20s, when they leave, would be in their early to mid-40s when they returned. They would have spent more than a decade in space. The radiation exposure over 14 years in deep space, with only modest shielding, is a concern that current radiation limits do not accommodate. Career radiation limits for NASA astronauts are set by age and sex based on a lifetime cancer risk threshold. The limit is designed to ensure that spaceflight does not increase an astronaut's lifetime cancer risk by more than 3%. A crewed Saturn round trip would likely require new risk frameworks, new approaches to shielding, or some combination of both. This is not an insurmountable problem. It is a real one. The food for a 14-year crewed mission cannot be entirely pre-packaged. No feasible spacecraft could carry 14 years of food for 6 people. A crewed Saturn mission would require a functioning agricultural system. Growing food in space is not a new idea. Plants have been grown on the space station for experimental purposes. The challenge for a Saturn mission is scale. You need to produce a significant fraction of the crew's caloric needs from onboard cultivation. You need to do this reliably over a decade and a half. You need the cultivation systems to be redundant, because crop failures in a closed system are serious. And you need to manage the nutrient cycles, the recycling of waste products back into growing medium without any external inputs. Closed-loop food production for long durations is one of the engineering challenges that mission architects spend serious time on. It is not solved in a form ready for deployment on a crewed outer solar system mission. The communication delay at Saturn's distance ranges from about 1 hour and 11 minutes to about 1 hour and 25 minutes one way. Nearly 3 hours from question to answer. Real-time communication is impossible. The crew cannot consult with Earth specialists in any meaningful real-time sense. Every technical problem is solved with what they know and what they carry. Saturn itself, like Jupiter, has no solid surface. Its bulk density, as noted, is lower than water. The entire planet would float in a large enough ocean. Within its atmosphere, pressures and temperatures increase with depth until hydrogen transitions through a liquid metallic phase under extreme conditions. There is no surface. There is nowhere to land. The entire focus of a Saturn mission is the Moon system. Saturn has 274 confirmed moons, more than any other planet in the solar system. Titan and Enceladus are the primary scientific targets. Titan orbits at about 759,000 miles from Saturn's center. Its atmosphere is 1.5 times denser than Earth's at the surface. It is composed mostly of nitrogen, with methane and complex organic molecules precursors to the chemistry of life. Titan's surface is covered by a thick layer of organic material called tholin reddish-brown hydrocarbon compounds that fall from the atmosphere continuously. The landscape includes mountains of water ice, river channels carved by liquid methane, and seas of liquid hydrocarbons. The largest sea, Kraken Mare, is comparable in size to the Caspian Sea. Titan is simultaneously one of the most alien environments in the solar system and one of the most scientifically compelling. Its organic chemistry is running at low temperature, driven by solar ultraviolet radiation and Saturn's magnetosphere, producing complex molecules that may give us insight into the chemistry that preceded life on early Earth. NASA's Dragonfly mission is a nuclear-powered rotorcraft designed to fly on Titan. Rotorcraft work in Titan's dense atmosphere. Despite the cold and low gravity, the combination of density and low surface gravity actually makes flight easier in some respects than in Earth's atmosphere. Dragonfly plans to fly between landing sites, covering tens of miles, sampling different geological terrains, and performing chemical analysis at each location. It is planned to launch in the late 2020s and arrive around 2034. It will be the first aircraft to fly on the surface of another world outside Mars. Enceladus, at about 148,000 miles from Saturn's center, is the other exceptional target. It is a small moon, about 313 miles in diameter, with a surface of nearly pure water ice that reflects almost all the sunlight that hits it. In 2005, Cassini discovered active geysers at Enceladus's south pole plumes of water vapor and ice particles erupting hundreds of miles into space. These plumes feed Saturn's E-ring with fresh material continuously. The water, being ejected, comes from a subsurface liquid ocean. Cassini flew through the plumes and analyzed their composition. Water, salt, carbon dioxide, methane, molecular hydrogen, complex organic molecules, including some amino acid precursors. The molecular hydrogen is particularly significant. On Earth, molecular hydrogen is produced by hydrothermal activity, the interaction of hot water with rock minerals, in a process called serpentinization. On Earth's ocean floor, this process creates hydrothermal vent environments that host rich biological communities independent of sunlight. The presence of molecular hydrogen in Enceladus's plumes strongly implies that hydrothermal activity is occurring on Enceladus's seafloor. That means chemical energy. That means the fundamental ingredients for life as we know it. Water, check. Chemical energy, check. Organic molecules, check. Stability over geological timescales, check. What we do not have is evidence of life itself. But Enceladus is, alongside Europa, one of the most compelling places in the solar system to look, and it is 6 years away. Uranus orbits the Sun at about 1,783,000,000 miles. A conventional Hohmann transfer from Earth would take about 16 years. Gravity assists can cut that dramatically. Only one spacecraft has ever visited Uranus. Voyager 2 passed it in January of 1986, about 8.5 years after its 1977 launch. using the speed it had picked up from Jupiter and Saturn along the way. Voyager 2 spent about 5.5 hours in the close vicinity of Uranus before continuing outward. 5.5 hours. That is everything we have from direct observation. No orbiter, no atmospheric probe, no lander, no extended study. Just a single flyby at high velocity, instruments running as fast as they could record as the spacecraft crossed through the system. And what that brief encounter revealed was a deeply strange world. Uranus's axial tilt is 97.8 degrees. The planet rolls around the Sun on its side. One pole points toward the Sun for roughly 20 years, while the other sits in complete darkness. Then, as Uranus completes its 84-year orbit and moves to the other side of the Sun, the poles reverse. The seasons on Uranus are extreme in a way that has no analogue anywhere else in the solar system. The North Pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. The South Pole gets the same, offset by half an orbit. The equatorial regions experience relatively rapid day-night cycles. The atmospheric dynamics that result from this unusual geometry are complex and poorly understood, because we have almost no data. Uranus has the coldest planetary atmosphere in the solar system, despite not being the farthest planet from the Sun. Its upper atmosphere reaches temperatures of about -371 degrees Fahrenheit, which is about -224 degrees Celsius. Neptune, farther from the Sun, is actually warmer than Uranus in its upper atmosphere. This is another Uranian mystery. Uranus appears to have very little internal heat, unlike Jupiter, Saturn, and Neptune, which all radiate more energy than they receive from the Sun. Uranus radiates almost exactly the amount of energy it receives. The mechanism that suppresses Uranus's internal heat release is not understood. Some hypotheses involve a layer within Uranus's interior that prevents the internal heat from reaching the surface. What creates such a layer, and why it exists on Uranus, but not the other ice giants, is unknown. Uranus's magnetic field is offset from the planet's center by about 30% of its radius and tilted about 60 degrees from its rotation axis. This creates one of the most asymmetric and complex magnetospheres in the solar system. As Uranus rotates, the magnetic field wobbles in a complex pattern rather than presenting a steady, symmetric structure like Earth's or Jupiter's. The 28 known moons of Uranus are all named after characters from Shakespeare and Alexander Pope. The 5 largest Miranda, Ariel, Umbriel, Titania, and Oberon may harbor liquid water oceans beneath their icy surfaces. A reanalysis of Voyager 2 data published in 2023, combined with thermal modeling, suggested that Ariel, Umbriel, Titania, and Miranda could all have subsurface liquid water oceans kept warm by radiogenic heating from decay of radioactive elements in their rocky interiors. If this is correct, Uranus's moon system may contain multiple ocean worlds. Miranda is particularly striking. Its surface is a geological patchwork that suggests a violent history. It has cliffs called Verona Rupes that may be the tallest cliffs in the solar system, dropping about 12 miles from top to bottom. In Uranus's low gravity, a rock falling off the edge of Verona Rupes would take about 10 minutes to reach the bottom. Miranda also has strange polygonal features called coronae, regions of unusual terrain that suggest ancient geological activity of a kind not seen elsewhere. The Planetary Science Decadal Survey, published in 2022, identified an Uranus orbiter and probe as the top priority for the coming decade. A mission concept called the Uranus orbiter and probe was recommended for development. If funded in the mid-2020s and built on a reasonable schedule, it might launch in the mid-2030s and arrive at Uranus around 2045, about 20 years from now. And that is a robotic mission. A crewed mission to Uranus, 9.5 years each way, puts the total round trip at roughly 20 to 25 years. An astronaut who left in their mid-30s would return in their mid to late 50s, having committed the majority of their adult working life to a single mission. The communication delay at Uranus's distance is approximately 2 hours and 37 minutes to 2 hours and 40 minutes one way. 5+ hours for any real exchange. The crew is alone in any meaningful operational sense. There is no help from Earth that arrives in time for an emergency. There is only the crew, what they know, and what they carry. Neptune is the last of the 8 planets. It orbits the Sun at about 2,793,000,000 miles. A conventional Hohmann transfer from Earth would take about 30 years. Voyager 2 reached Neptune in August of 1989, 12 years, and 1 day after its launch, in August of 1977. It used gravity assists from Jupiter, Saturn, and Uranus in sequence the Grand Tour trajectory that required a once-in-175-year alignment of the outer planets. And that cut the flight time to Neptune from about 30 years down to 12. The next such alignment won't occur until the 2200s. No mission has been to Neptune since Voyager 2's flyby. Every image we have of Neptune close up was taken in those few hours in 1989. Neptune is a beautiful planet. Its deep blue color comes from methane absorbing red wavelengths and reflecting blue. The Voyager flyby revealed a planet with extraordinary atmospheric dynamics. Wind speeds in the atmosphere reaching more than 1,200 miles per hour, faster than the speed of sound at Earth's surface. Storms that appear and disappear on timescales of years to decades. The Great Dark Spot observed by Voyager was comparable in scale to Earth. When the Hubble Space Telescope observed Neptune years later, the Great Dark Spot was gone. Neptune's atmosphere is more dynamic than almost any other planetary atmosphere we have observed. Neptune has 16 known moons. Triton is the largest and most remarkable. Triton orbits Neptune in a retrograde direction opposite to Neptune's rotation. This is essentially impossible for a moon that formed in place around Neptune. Retrograde moons are almost always captured objects. Triton is believed to be a former Kuiper Belt object, captured by Neptune's gravity early in the solar system's history. The capture event would have been violent and dramatic. Triton, entering Neptune's gravitational influence on a hyperbolic trajectory, being slowed by gravitational interactions over time until it settled into its current, roughly circular, retrograde orbit. This process would have taken millions of years and would have cleared out most of Neptune's original moon system. Original moons would have been perturbed by Triton's orbit and flung away or destroyed. The irregular moons that remain are likely the remnants of that original system or captured objects from later. Triton's surface temperature is about -391 degrees Fahrenheit, which is about -235 degrees Celsius among the coldest surfaces measured in the solar system. Despite this extreme cold, Voyager observed active geysers. Nitrogen geysers erupting from the surface and rising miles into the thin atmosphere before being carried downwind. The mechanism is sunlight, even at Neptune's distance. Solar radiation warms Triton's thin nitrogen ice, creating pressure that eventually erupts through the surface as a geyser. Active geology. Active geological processes. On a world this cold, this far from the sun, it is a reminder that the solar system does not conform to simple expectations. There is life. Well, geological activity, finding its way in the most improbable conditions. A crewed mission to Neptune and back spans 25 to 30 years. The communication delay is about 4 hours and 9 minutes one way. 8+ hours for any real exchange. The crew is not just autonomous. They are, by any practical definition, an independent civilization of 6 to 8 people traveling through the outer solar system. The numbers for each planet ask something of you. They ask you to sit with what they actually mean. Not the headline 12 years to Neptune, but the weight of it. 12 years. In a spacecraft, with a small crew, moving through a solar system that is mostly empty space and extreme cold and silence. The technological gaps that stand between us and crewed outer solar system missions are real. The rocket equation governs them with mathematical precision. The rocket equation says that the mass ratio between a fully fueled spacecraft and an empty spacecraft must scale exponentially with the velocity change required. Double the velocity change you want to execute, and the mass ratio is squared. Triple it, and the ratio is cubed. This exponential relationship means that, at some point, adding more fuel stops helping. You're adding so much fuel that most of the fuel is used to accelerate the fuel itself. The most efficient chemical rockets, liquid hydrogen and liquid oxygen, achieve a specific impulse of around 450 seconds. Specific impulse is the measure of how efficiently a rocket engine uses its propellant. Higher is better. Chemical rockets are at roughly their theoretical limits. Nuclear thermal propulsion, which heats propellant by running it through a nuclear reactor, achieves a specific impulse of about 800 to 900 seconds, roughly twice the efficiency of the best chemical rockets. NASA and DARPA have been funding nuclear thermal propulsion development through a program called Draco Demonstration Rocket for Agile Cislunar Operations. A flight demonstration is planned for the late 2020s. If nuclear thermal propulsion reaches operational maturity, it roughly halves transit times for a given mission. A 9-month Mars transit becomes approximately 4 to 5 months. A 3-year Jupiter transit becomes around 16 to 18 months. Ion drives, which achieve specific impulses of 3,000 to 10,000 seconds or more, are far more efficient. But their thrust is tiny. An ion drive on a crewed mission would take years to achieve the velocity change that a nuclear thermal rocket achieves in hours. Hybrid architectures combine them: high-thrust nuclear thermal or chemical propulsion for departure and arrival maneuvers, ion propulsion for the long coasting phases. This is one of the architectural approaches being studied for human missions beyond Mars. Beyond these near-term options lies fusion, propulsion, still theoretical for spacecraft, but physically plausible. A fusion drive could achieve both high thrust and high specific impulse simultaneously, the combination that neither chemical nor current ion propulsion provides. Fusion propulsion could potentially reduce Mars transit times to weeks, Jupiter transit times to months, Saturn transit times to 1 to 2 years. This would transform the outer solar system from a destination requiring multi-decade commitments to one accessible within single career missions. But fusion propulsion for spacecraft is not a solved engineering problem. The physics of fusion energy were cracked experimentally in December of 2022 when the National Ignition Facility achieved ignition more energy out than laser energy in. But translating that milestone into a propulsion system for a spacecraft involves solving many additional engineering problems at the same time. It is the technology that would change everything. It is not near. There's a dimension of these transit times that doesn't appear in the propulsion equations. The person, the human being inside the metal capsule. There is a moment in every planetary transit, mission planners account for it. Astronaut trainers prepare crews for it when the spacecraft reaches the point in the journey where it is equidistant from Earth and the destination. For a Mars mission at 8 months, that's about 4 months in. For a Jupiter mission at nearly 3 years, that's around 18 months in. It's the point where Earth is the same distance as where you're going. Neither closer nor farther. Just equidistant. And that moment has a psychological weight that is hard to convey in technical terms. Before that midpoint, if something goes badly wrong, returning to Earth is the geometrically shorter option, the abort mode. After it, continuing forward is geometrically equivalent to going back, and often the operationally preferred choice. The mission has its own momentum. Not just the physical momentum of the spacecraft. The human momentum of a crew that has been living this mission for months and is increasingly committed to seeing it through. Astronauts who have spoken about extended space missions often describe a gradual shift in psychological orientation. Early in the mission, Earth is still psychologically present. You can see it. It fills a portion of the sky. Communication delays are minutes. Home still feels real. But as weeks turn to months, Earth shrinks. The communication delay grows. Responses from Earth take longer. The news from home begins to feel like dispatches from a place you used to live, rather than a place you belong to right now. The spacecraft becomes your world. Its rhythms, its sounds, its small spaces and familiar smells. The crew members around you are not colleagues in the ordinary sense. They are your entire social universe. Your only real-time human contact. Your family, your co-workers, your community, all compressed into the same small group of people you see every single day. This psychological shift is expected. It has been observed and documented in Antarctic winter over crews who spend months in extreme isolation at polar research stations, in submarine crews on long deployments, in experimental isolation studies designed to simulate deep space mission conditions. The research from these environments informs deep space mission design in concrete ways. Crew selection for psychological compatibility, not just individual resilience. Autonomous scheduling authority, giving crew members meaningful control over their work and personal time. Communication, privacy, individual private communication windows with family on Earth, not monitored by other crew members. Meaningful tasks and goals, not busy work. Genuine autonomy in decision-making. These are mission-critical design elements. They are as important as the propulsion system. An international study called Mars 500, conducted between 2010 and 2011 at the Institute for Biomedical Problems in Moscow, isolated 6 crew members in a mock spacecraft for 520 days. The simulated duration of a Mars mission. The crew members didn't go anywhere physically. They lived in a series of interconnected modules in Moscow for a year and a half. The findings were instructive. The crew members maintained adequate function throughout the mission. But detailed analysis showed that most of them became progressively more sedentary over time. They slept more. They exercised less. Several developed disrupted sleep rhythms. One crew member showed signs of significant psychological withdrawal. The researchers noted that the patterns observed were similar to those seen in depression. Not in a clinical sense necessarily, the crew maintained their function and relationships. But the absence of meaningful environmental variation, of natural light cycles, of genuine social diversity, of the ability to go outside, produced changes in behavior that suggest the environment was psychologically taxing in ways that the standard psychological assessments didn't fully capture. This is important. Mars 500 was 520 days. A real Mars mission is roughly 1,000 days from departure to return. A Jupiter mission is roughly 3,000 days. A Saturn mission is more than 5,000 days. These numbers are in a different category from anything studied. The honest answer is that we don't know how human psychology responds at those extremes. We have data that goes up to 6 months on the space station. We have the Mars 500 study up to 500 days in a simulated environment. We do not have data beyond that. We are, in that sense, flying genuinely into the unknown on the human side of mission planning. There is something worth recognizing about where we are in this process. Every number in this story, every transit time, every radiation dose, every Hohmann trajectory, every specific impulse was calculated by people who have never left Earth. Every mission we have sent to every planet was designed, built, launched, and operated by people standing on the ground. Pioneer, Voyager, Cassini, New Horizons, Mars Pathfinder, Curiosity, Perseverance, all of it. No humans have been beyond the moon. No human has experienced what a 7-month transit feels like in actual deep space. No human has seen the asteroids belt from inside it. No human has seen Jupiter up close through a window. No human has experienced the communication delay of Neptune. Everything we know about these places comes from instruments, cameras, spectrometers, magnetometers, particle detectors, instruments that can record measurements and transmit them back to Earth. But that cannot convey the experience of being there. When the first humans travel to Mars and stand on its surface, they will experience something that no instrument can measure: the weight of the sky, the color of the dust, the sound of Martian wind faint because the atmosphere is thin but real, the stars at night from a sky with no light pollution and an atmosphere too thin to scatter starlight the way Earth's does. The fact of standing on a world that is not Earth, with Earth nowhere visible overhead, somewhere behind the horizon or on the other side of the planet. These are not scientifically measurable quantities, but they are real. They will matter to the people who experience them, and they are things that can only be known by going. The transit time is the price of that knowledge. Whatever it is, months, years, decades, it is the price. The question that every generation of potential Mars astronauts has to answer for themselves is whether the knowledge and the experience are worth the price? History suggests they will answer yes. They always have. The planets themselves, when we finally send humans to them, will tell us things we cannot know from a distance. Not metaphors. Actual things. Mars's subsurface geology holds a record that its robots have only begun to read. The InSight lander, which operated on Mars from 2018 to 2022, was the first geophysical station on another planet. It measured Marsquake seismic events in Mars's interior using a seismometer placed directly on the surface. InSight detected hundreds of Marsquakes during its mission. The data revealed that Mars has a liquid outer core, a rocky mantle, and a crust that varies in thickness from about 12 miles to about 25 miles. This seismic picture of Mars's interior is one of the most significant scientific returns of the entire Mars exploration program. A crewed mission could emplace a network of seismometers across Mars, could drill into the subsurface to reach depths that no current robotic mission can access, could collect samples from sites selected in real time based on what the drill reveals. The potential scientific return from human presence on Mars is qualitatively different from robotic exploration. Not because humans are smarter than robots in many respects, modern robotic systems are extraordinarily capable, but because humans can adapt on the fly. A geologist standing next to an interesting rock outcrop can see relationships and make decisions in seconds that would take months to plan, uplink, execute, and receive results for in a robotic mission with a round-trip communication delay. Human presence on Mars is not just about symbolism. It is about a different mode of scientific investigation. Jupiter's moons represent the outer solar system's greatest scientific prizes. Europa's ocean is the obvious headline. But Ganymede, the largest moon in the solar system, larger than Mercury, has its own subsurface ocean and a magnetic field, the only moon known to have one. The interaction between Ganymede's magnetic field and Jupiter's enormous magnetosphere creates a system that scientists are still working to fully understand. Io is the most volcanically active body in the solar system. More volcanic activity than anywhere else we have observed. Its surface is continuously resurfaced by lava flows. Some of its volcanic plumes rise over 200 miles above the surface. The heat comes from tidal, flexing the same gravitational interaction with Jupiter that heats Europa's ocean from below and keeps Enceladus's ocean liquid. Io represents tidal heating at its most extreme. If you want to understand the volcanic and tectonic processes that shaped the early Earth and the early planets, Io is a living laboratory. Callisto's ancient cratered surface is a geological record going back to the earliest epochs of the solar system. The 4 Galilean moons together represent a compressed history of planetary formation, geological activity, and ocean worlds sitting in a system you can reach in under 3 years. Saturn's moon system has its own scientific depth. Titan's atmosphere is the best available laboratory for prebiotic chemistry, the chemistry that preceded life on early Earth. Complex organic molecules are forming continuously in Titan's atmosphere, raining down onto the surface, potentially accumulating in the hydrocarbon lakes. Understanding the chemistry of Titan's environment may tell us more about the origin of life than any other environment in the solar system outside Earth. Enceladus's ocean chemistry, as sampled by the Cassini flybys, reveals conditions that our best models say should be favorable for life. Whether life actually exists, there requires in situ investigation that Cassini couldn't provide. The transit times are the entry costs. The The scientific contents of these destinations are the reason to pay them. It is worth considering what these missions would actually look like in organizational terms. Who designs them? Who funds them? Who selects the crews? Who decides when the risks are acceptable? These are not purely technical questions. They are questions about how a civilization organizes itself around an audacious long-term goal. The Apollo program, for context, ran from 1961 to 1972. It employed roughly 400,000 people at its peak. It consumed about 4% of the United States federal budget in its peak years. It accomplished the first human landing on the moon in 8 years, from Kennedy's declaration to Armstrong's step. 8 years, from a standing start. That achievement required a level of national focus and resource commitment that has not been replicated since. The current pace of human space exploration is slower, more distributed across agencies and private companies, and more constrained by budget realities. NASA's Artemis program, aimed at returning humans to the moon, has been in development since around 2019 and has faced multiple delays, budget pressures, and technical challenges. A crewed lunar landing is now projected for the mid to late 2020s. The moon is 3 days away. The organizational and political challenges of sustaining a multi-decade effort for a Mars mission, let alone an outer solar system mission, dwarf those of Artemis. A Mars mission requires sustained commitment across multiple political administrations, multiple national budgets, and probably multiple decades of development. Each administration that takes power can change priorities. Each budget cycle can reduce funding. The technology that was being developed can be cancelled and restarted. This is not a hypothetical concern. It has happened repeatedly in the history of human space exploration. The Space Exploration Initiative, announced by President George H.W. Bush in 1989, proposed a return to the Moon and eventual missions to Mars. The program was never funded adequately and was abandoned. The Constellation program, announced by President George W. Bush in 2004, aimed to return humans to the Moon and then Mars. It was cancelled by the Obama administration in 2010. Vision for space exploration, Constellation, Artemis the Moon has been the stated goal repeatedly. We have not been back since 1972. Mars is harder than the Moon. The transit time is longer. The mission duration is longer. The technology gaps are larger, and the political will required to sustain the effort across the decades needed to develop it is something that no democracy has demonstrated. Over that timescale, for a space program, this is the honest context in which the transit times exist. They are not just physics problems. They are civilization problems. Can a civilization organize itself to commit to a goal that requires decades of consistent investment, that will produce its most dramatic results long after the people who initiated it are gone from power? Space programs can. Scientific programs can. The Voyager missions were proposed in the early 1970s and are still operating. Cassini was proposed in the 1980s and operated into 2017. The James Webb Space Telescope was proposed in the 1990s, funded intermittently, built over years, and launched in 2021. These programs succeeded because they were driven by scientific communities that maintained their advocacy across political cycles, that produced results that justified continued investment, and that adapted to changing budgets while keeping the core mission alive. a crewed Mars program would need similar persistence. A crewed outer solar system program would need even more. The private sector changes the picture somewhat. SpaceX, Blue Origin, and other commercial companies have introduced competitive incentives and private capital into space transportation in ways that were not present during the Apollo era. SpaceX, in particular, has stated explicit ambitions toward Mars colonization. Whether private companies can sustain the investment required for Mars mission development and whether they can execute safely at the level required for human missions remains to be demonstrated. The transit time doesn't change based on who pays for the mission. But the organizational structure that sustains the effort across the decades needed to make it possible is a variable that is as important as any engineering challenge. There is also the question of what a crewed presence at each planet actually enables beyond the scientific gains. The romantic argument for human space exploration, the expansion of civilization, the survival of the species. The intrinsic value of exploration is real, but often treated as secondary to the scientific justification. In the framework of transit times and mission architectures, it is worth asking what becomes possible when humans actually get to each of these destinations and stay. Mars is the obvious case, because it has been studied most extensively. The argument for permanent human presence on Mars rests on the idea that Earth's civilization exists on a single fragile planet, and that distributing humanity across two planets reduces the existential risk from any catastrophe that could threaten life on one. This argument is made by serious people with serious scientific credentials. It is also an argument that requires accepting that the transit time to Mars, 7 to 9 months, with a stay of over a year, makes regular two-way traffic difficult for a very long time. The people who go to Mars as early permanent settlers are making a commitment that is qualitatively different from a mission crew. They are not just accepting the transit time for a mission. They are accepting the transit time as a fact of their permanent life situation. They may return to Earth occasionally if round-trip traffic becomes routine. They may not return at all. The first permanent Mars settlers, if there are any in the next century, will have accepted that Mars is their home and Earth is a place they came from. This changes the nature of what a Mars transit time means. It is no longer the cost of a round trip. It is the cost of the original crossing. Like people who crossed an ocean centuries ago, knowing the return trip was possible in principle, but unlikely in practice. They arrived. They stayed. They became the people of that place. And their descendants, over generations, became genuinely different in culture, perspective, and eventually in the things that matter most, what they knew, what they built, what they valued. A Martian civilization would be in that lineage. Not a colony in the colonial sense of exploitation from afar. A real outpost of human civilization. Self-governing, self-sufficient in time, self-defining, in ways that Earth cannot dictate across a communication delay of 3 to 22 minutes. This is not inevitable. It is possible. Whether it happens depends on whether the transit time is paid in the first place. And whether the transit time gets paid depends on whether the technology develops, whether the will exists, and whether the specific people who would make the journey choose to do it. For the outer solar system, the permanent settlement question is more distant. The transit times make permanent human settlement of the Jupiter or Saturn moon systems, something that can barely be discussed in concrete terms yet. 6 years to Saturn. For anyone who settles there to maintain connection to Earth, to the broader human civilization, would require accepting communication delays of over an hour and physical transit times of years. A community of people living at Titan or Enceladus would be more genuinely independent of Earth than any human community has ever been. Not just in physical distance, in information lag. Any decision that requires information from Earth, political, economic, technical, is a decision where the most recent information available is an hour and a half old at minimum. Any crisis that requires Earth's help is a crisis where Earth won't even know about it for over an hour. Such a community would need to be comprehensively self-sufficient in governance, in resource production, in medical care, in technology maintenance, in culture, in the reproduction and education of the next generation. It would be a civilization, small, isolated, but in every functional sense, its own. The transit time makes it that. Not because the people would choose disconnection, because the physics of the solar system enforces it. There is one more thing worth saying about the transit times to the outer solar system. These distances, as enormous as they are nothing compared to what lies beyond. Proxima Centauri, the nearest star to our Sun, is about 4.24 light-years away. 1 light-year is about 5,870 billion miles. Proxima Centauri is about 25 trillion miles from Earth. Voyager 2 reached Neptune in 12 years. A Hohmann transfer to Proxima Centauri, if such a thing were calculable, would take tens of thousands of years. Voyager 1, the most distant human-made object, is traveling at about 38,000 miles per hour. At that speed, it would take about 73,000 years to reach Proxima Centauri. Not 12 years. 73,000 years. These numbers put the transit times we have been discussing in a different context. Neptune, 12 years away, is practically in Earth's backyard compared to the nearest star. The entire solar system, from Mercury to the theoretical outer edge of the Oort cloud, is a compact neighborhood sitting in the enormous emptiness between stars. The distances within the solar system are genuinely large. They require new technology and enormous commitment to traverse with human crews. But they are the navigable part. They are what we can reach, with technologies that extend plausibly from what we already have. Everything beyond the heliopause, beyond the bubble of the sun's solar wind, out into the interstellar medium, toward other stars, requires something we don't yet know how to build. Not nuclear thermal propulsion, not fusion drives. Something that can sustain relevant velocity for decades at minimum. Possibly a laser sail driven by a focused beam from an Earth-based installation. Possibly an antimatter drive. Possibly something not yet conceived. The planets are the achievable frontier. The stars are a longer horizon. What we do with the planets, how we learn to travel to them, live in transit to them, operate near them, sustain human life in the environments around them, will be the foundation for everything that comes after. The transit times we are dealing with now are the school. The mastery of deep space travel within the solar system is the prerequisite for anything beyond it. There is also the matter of what these missions mean for the humans who do not go. The vast majority of people, in any era of space exploration, do not go. They watch. They read. They follow the missions through the instruments and cameras and data returns that the spacecraft transmit back. When Voyager's cameras turned around in 1990 and photographed the solar system from beyond the outer planets, Carl Sagan wrote about the pale blue dot Earth. visible as a tiny point in a sunbeam in the wide-angle image. A point of light containing all of human history to that moment. Every person who ever lived. Every war. Every art. Every discovery. On a speck. That image changed something for many people who saw it. Not because they went anywhere. Because the perspective it offered, this is where we are. This is how small it is. This is what it looks like from the outside, was genuinely new. Every mission to every planet produces this kind of new perspective. Cassini's images of Saturn's rings from within the ring plane, the first close-up photographs of Pluto from New Horizons, the heart-shaped nitrogen ice plain, the mountains of water ice, the haze of the thin atmosphere. These images are not just scientific data. They are new things the human species has seen. New places that exist in our shared imagination because someone built a machine capable of reaching them and sending back what it found. The transit times make these images possible. 9 years from Earth to Pluto. 35 years from Earth to the heliopause. 6.5 years to Mercury orbit. These are the prices paid for every image, every spectrum, every measurement that has come back from the solar system's exploration. The first human photographs taken from Mars's surface will carry that same weight, not just for the scientists who designed the mission and analyzed the data, for everyone who looks at them, because they will show something that has never been seen by human eyes. The Martian sky, the Martian horizon. The Earth in the Martian sky, a point of blue light, 2/3 the angular size of the Moon, as seen from Earth, visible in the pre-dawn or post-dusk sky. These are things that don't exist yet in human experience. They will exist after the mission. The transit time is part of what makes them worth waiting for. There is a long view and a short view on all of this. The short view sees the transit times as obstacles, barriers between what we want to know these worlds intimately, to stand on them and study them and build things there, and what we can currently do. The long view sees the transit times as the structure of the problem, the thing that organizes everything else. If the transit to Mars were instantaneous, a crewed Mars mission would be trivial. Build a ship, teleport, study, come home. But it isn't instantaneous. It is 7 to 9 months. And that fact drives the entire architecture of Mars mission planning. The radiation shielding, the exercise protocols, the medical systems, the food supply, the psychological support, the crew selection, the stay time constraint. All of it flows from the transit time. The transit time is not just an obstacle. It is the generator of the problem. And the problem, as engineering problems go, is one of the richest and most interesting that exists. Because solving it, at each level, at Mars, at Jupiter, at Saturn, unlocks something genuinely new. Not just for the scientists, for us, for the species. We live in a solar system, not just on a planet in a solar system. We live in it. We have touched with instruments, with cameras, with the atoms of our curiosity and ingenuity every planet, every major moon of every outer planet, comets and asteroids and distant Kuiper Belt objects. We have put ourselves at the edge of interstellar space with 2 small machines launched nearly 50 years ago that are still transmitting. The transit times are real. The distances are real. The difficulty is real. And all of it is within the same solar system we have been exploring since the first satellite launched in 1957. One step at a time. One transit at a time. One planet at a time. The asteroid belt deserves more attention than it gets in discussions of planetary travel. Most people think of the asteroid belt as an obstacle between the inner and outer solar system. That is the science fiction version. The reality is that the belt contains objects that are among the most scientifically interesting and economically significant bodies in the solar system. Not despite being debris, because of it. The asteroids are the raw material from which the inner planets formed. The rocky, differentiated asteroids, Vesta being the most dramatic example, are fragments of planetary embryos that never completed their formation, disrupted by Jupiter's gravitational influence before they could coalesce into a full planet. Studying Vesta up close, which the Dawn mission did in orbit from 2011 to 2012, is essentially studying the interior of a planetary embryo. Vesta has a core, a mantle, a crust. It differentiated, separated into layers by density during a period when it was molten just as Earth did. It then suffered a massive impact that excavated a crater so large it exposed the mantle. Rock from Vesta's interior was thrown into space by that impact. Some of it eventually reached Earth as meteorites, a specific class of meteorites called HED, meteorites that isotopically match Vesta's material. Dawn confirmed this connection beyond any doubt. We have pieces of Vesta in our museums and laboratories, pieces of an ancient planetary embryo. The transit time to the main asteroid belt for a crewed mission ranges from about 1 to 2.5 years, depending on the target. Some near-Earth asteroids, as noted, are energetically more accessible than the Moon. The asteroid redirect mission, now cancelled, studied a crewed mission to a near-Earth asteroid as a stepping stone toward Mars. The scientific and resource extraction potential of the asteroid belt is one of the arguments that serious space economists make for investing in solar system infrastructure. Platinum group metals in concentrations that dwarf anything on Earth's surface. Water ice that can be converted to rocket propellant. Iron nickel in quantities that make Earth's metal reserves look modest. The transit to the belt is not trivial, but it is within the range of missions that near-future human spaceflight can contemplate. It is, in some respects, the next step after Mars on a practical roadmap toward the outer solar system. You learn to operate in deep space. You learn to use in-situ resources. You develop the technology and the institutional knowledge. And then you go farther. The communication delays associated with each planetary distance shape not just the logistics of missions, but the fundamental relationship between Earth and any crew that travels beyond a certain threshold. At the Moon, the communication delay is about 1.25 seconds each way, 2.5 seconds round trip. Essentially, real time. You can have a conversation. Mission Control can monitor and respond in near real time. The Apollo crews were tightly connected to mission controllers in Houston throughout their missions. At Mars, the delay ranges from about 3 minutes to 22 minutes each way, 6 minutes to 44 minutes round trip. A conversation becomes a correspondence. You ask a question. You wait at minimum 6 minutes for the answer. During a nominal mission, this is manageable. A crew that knows what they are doing and has the information and tools they need can operate autonomously. Mission Control is an advisor, not a director. But in an emergency, where things are changing faster than the communication window allows, the crew is effectively alone. At Jupiter, The delay reaches 33 to 53 minutes each way, over an hour and 40 minutes round trip at maximum distance. At Saturn, about 1 hour 11 minutes to 1 hour 25 minutes each way, nearly 3 hours round trip. At Uranus, about 2 hours and 40 minutes each way, over 5 hours round trip. At Neptune, about 4 hours and 9 minutes each way, over 8 hours round trip. These numbers define the operational reality of each mission. At Neptune, if a crew member becomes critically ill, the crew has to manage the situation entirely. By the time Earth even knows about it, the situation has resolved itself one way or another. Earth is informed, not involved. This level of operational autonomy is a different kind of challenge than humans have faced in spaceflight to date. Apollo, space station, even a near-future Mars mission, these all involve meaningful ongoing connection to Earth. Real-time support, consultation, the ability to uplink software patches, to receive advice from specialists, to have mission control, catch anomalies before the crew does. An outer planet mission is fundamentally different. The crew carries everything they need, in their training, in their tools, in their medical kit, in their knowledge. Earth is historical context and encouragement, not operational support. Mission designers know this and design accordingly. Artificial intelligence on board to help diagnose technical failures, comprehensive medical databases and decision support systems, extensive training in fields that would be handled by specialists on Earth, medicine, psychology, engineering, maintenance, agricultural management. The crew of an outer solar system mission would need to be among the most broadly capable humans ever assembled for a single task. Not the world's best at one thing, adequately good at everything. Specialists who cross-train, generalists who specialize. The deep generalist as the model for deep space. There is one more dimension that rarely gets discussed in the context of planetary transit times. What happens to space exploration after humans arrive? Every robotic mission to a planet produces a template, an understanding of the environment, the surface conditions, the atmospheric dynamics, the radiation levels, the potential hazards. This template is what makes subsequent missions possible. The first missions to Mars, Mariner 4's flyby in 1965, Viking's landing in 1976, established the basic parameters of the Martian environment. Every mission since has built on that foundation. Pathfinder proved that airbag landing was possible in Mars's atmosphere. Spirit and Opportunity proved that rovers could traverse significant distances and make geological discoveries. Curiosity proved that a nuclear-powered science laboratory could operate for years on the Martian surface. Perseverance proved that oxygen could be produced from the Martian atmosphere and that Martian soil samples could be drilled and cached for future return. Each mission raises the ceiling for the next. The first crewed Mars mission will be the foundation on which everything that follows is built. The knowledge gained from that mission, the actual experience of human physiology in Mars gravity for an extended period, the practical challenges of surface operations, the performance of life support and habitat systems in the actual Martian environment will be the database for every subsequent Mars mission. The same progression will happen at each planet. First, robotic. Then robotic, with more capability. Then human. Then human, with more capability. Over decades and centuries, the understanding deepens. The infrastructure develops. The transit becomes more routine, not necessarily shorter. The physics of the solar system don't change, but the organizational and technological infrastructure for making the trip becomes more mature, more reliable, more affordable in relative terms. The transit to Mars becomes what the transit to Antarctica is now, not trivial, but not extraordinary. Something that happens regularly, with regular logistics support, with crews that rotate in and out on reasonable timescales. We are not there yet. We are closer to the beginning of that progression than anywhere near the middle. But the progression is real, and it is already underway. Every Mars rover is part of it. Every Europa flyby is part of it. Every piece of technology demonstrated in low Earth orbit is part of it. The transit times to each planet are fixed by physics. The civilization that learns to pay them is not yet fully built. But it is building. Before we look up at those points of light one more time, it's worth acknowledging what this all adds up to. We have, as a species, sent spacecraft to every planet in the solar system. Every single one. From Mercury to Neptune, including Pluto, including multiple asteroids, including comets, including the heliopause itself. All of this was done with propulsion technology that is, at its core, not dramatically different from what Tsiolkovsky described mathematically in the early 1900s. Chemical rockets, gravity assists, careful trajectory design, patience. The probes we sent are tiny compared to any crewed vehicle. They need no life support, no food, no medical care, no psychological support. They don't care about radiation. They don't care about the transit time. They don't care about anything. They just travel, collect, transmit. And yet even these simple machines, unburdened by the needs of biology, took years to reach their destinations. 12 years to Neptune, 9 years to Pluto, 6.5 years to Mercury orbit. These are the travel times for the fastest, most fuel-efficient trajectories we can calculate, with the most patient engineering we can deploy. The physics doesn't compress for human convenience. It operates on its own schedule, and yet we keep sending, and we keep learning. And the case for eventually sending people with all the additional cost and complexity that biology demands grows stronger with every mission. Because what we get back from people will be qualitatively different from what we get from instruments. The instruments tell us what's there. The people will tell us what it means to be there. That distinction matters. When you look at the night sky on a clear evening, the planets are visible. Venus often blazes in the west after sunset, or in the east before dawn, bright enough under dark conditions to cast a faint shadow. Mars, near opposition, glows distinctly orange-red, brighter than all but a few stars. Jupiter hangs with a steadiness that stars don't have its disk resolved, even in binoculars, its 4 Galilean moons visible as tiny points of light arranged in a line. Saturn is visible to the naked eye as a yellowish point. Through a small telescope, the rings are immediately apparent and almost impossible to believe. They look too perfect, too geometric, like a diagram rather than a real thing. But they are real. Ice and rock in a flat plane, obeying the same laws of gravity as everything else, just doing so in a configuration that happens to produce one of the most visually striking objects in the solar system. Uranus is occasionally visible to the naked eye in very dark skies. Most people who see it assume it is a faint star. Neptune is not visible to the naked eye at all. 8 planets, each carrying a transit time now. Not as an abstraction, as a real cost, measured in years, measured in what those years mean for a human body and a human life. Mercury, months of transit, to a surface that tries to destroy everything that reaches it. Venus, 3 to 5 months, to a surface you cannot stand on with any technology we currently have. Mars, 7 to 9 months each way, and your life belongs to the mission for 2.5 to 3 years. Jupiter, nearly 3 years each way, and the most interesting targets are surrounded by radiation that kills electronics in hours. Saturn, 6 years each way, and the mission spans more than a decade. Uranus, 9.5 years each way, and the total commitment is 2 decades. Neptune, 12 years each way, and the math alone puts it in a different category of commitment than anything we have attempted. These are the honest numbers, not the optimistic ones from a funding proposal, not the impossible ones from a science fiction movie that doesn't care about orbital mechanics, not the pessimistic ones from someone who has given up. Just the physics, just the geometry, just the solar system, being exactly as large as it is, with exactly the laws of motion that govern it. The universe did not design itself for our convenience. The distances are not scaled to human lifetimes. The radiation environments were not arranged to be survivable without effort. The timescales of orbital mechanics do not align with the timescales of human patience. The solar system is indifferent, and the fact that we are here on this particular planet, with this particular biology, capable of looking out at those other worlds and asking these questions, that is not the universe accommodating us. That is us, working with what we have, pushing against limits that were not designed to move. Every mission we have sent outward was sent by a civilization that existed entirely on one small world with limited resources, and chose to use some of those resources to know what was out there. Not because it was profitable, not because it was safe, because not knowing felt worse than the cost of finding out. The people who go, when they eventually go, will know these transit times better than anyone alive. They will have lived with the numbers for years before departure, studied them, run the simulations, trained for the physiology and the isolation and the emergencies, made peace with what the timeline means for the people they are leaving behind. And then they will go anyway. Not because the numbers don't matter, because something else matters more. The thing that has always mattered more, in every era of exploration, every crossing of unknown water, every ascent of a summit that offered nothing except the view from the top. The need to know, the refusal to live out a life in comfortable ignorance when something real and specific and extraordinary is sitting out there. Patient, indifferent, not going anywhere. The physics has not changed since Newton described it. The distances have not shrunk. The laws of motion have not been suspended for our benefit. The planets will wait. They have been circling this star for 4.5 billion years. A few more decades of human hesitation means nothing to them. But it matters to us, because the people who would go are alive now, running the calculations now, building the technology now, making the case in budget proposals and scientific papers and engineering design reviews for why the transit time is worth paying. The funding will be in place. The crew will be trained. The launch window will be approaching. And at some point, The calculations will be complete enough. The technology ready enough. The window open, and the transit time will start counting down. Not on a diagram, in real seconds, one at a time. The transit time will start counting down, not on a diagram, in real seconds, one at a time. For the first person who will cross this solar system, those seconds have already begun. They just don't know it yet. Good night.